Okay, let's talk a little bit about section 4.1. We're going to talk about the general properties of aqueous solutions. Now, the general properties we're going to talk about are very specific. They have to do with the idea of solubility. So the idea is, does something dissolve in water? So if you think about it, we have experience dealing with things that dissolve in water. We know that table salt dissolves in water, right? Now, do you know what the chemical formula for table salt is? It's sodium chloride is the name of the compound. And the chemical formula is NaCl. What's another type of thing that dissolves in water? Sugars, right? So sugar does. Sugar is actually what's called sucrose, and it has the chemical formula C12H22O11. Turns out, even though both of these two substances dissolve into water, and it looks almost the same when they do, in fact, they both look like little, white crystals that are granulated. They dissolve pretty much the same. It looks the same. It turns out they're very different substances. Sodium chloride is what's called a ionic compound. Whereas sucrose is a molecular compound. And functionally, these are very different substances. Ionic compounds are made up of alternating combinations of positively charged particles and negatively charged particles. So this would be perhaps thinking about the top surface of a grain of salt, with the sodium ions being positively charged and the chloride ions being negatively charged. So alternating positive and negative ions. So below that first level, the surface level, there's another layer of ions, just like the first layer. And I'll just draw a few of them right there. So that's what we would expect for an ionic compound, the sodium chloride being an ionic compound. The metal atoms are usually positive ions. So sodium is a cation, meaning it's positive, and chloride is an anion, meaning it's negative. So what goes on when you dissolve salt into water? Essentially what occurs is water molecules are able to rip these ions off the surface and pull them into the water, into the bulk of the water. The water molecules are attracted to these ions, and they can rip them out, and then over time, the salt crystal gets smaller and smaller and smaller and smaller. Okay? So let's do the following. Let me get rid of some of this. So the idea is that the water molecule has 3 atoms. And for reasons that I won't go into right now, it turns out the oxygen atom has a negative charge, and the hydrogen atoms have a positive charge, which exists in between the 2 atoms. There's a positive there. This creates what's called a dipole. And so what happens is that negative charge, if it gets anywhere near a positive charge, and the sodium ion is positively charged, the water molecule, the positive negative charges will interact electrically. It's an electrical attraction. And so what can happen is when you put salt into water, the water molecules are liquid, right? liquids are able to move around, rotate, and change their positions. So the water molecules will orient themselves so that the oxygen atoms can all interact with the sodium ion that's in the crystal and the surface of the crystal. And interact with it and actually pull it off of the crystal. Think about it. All those chloride ions are negatively charged. They're trying to hold the sodium ion in the salt. And they do a pretty good job of it under normal circumstances, unless you put it into water. Water molecules will work together as a team. I'm showing 4 water molecules there, but there's actually be 6 of them. There'd be one coming up above and then one below for a total of 6. And enough of these water molecules could interact to essentially rip the sodium ion away from the sodium chloride. Likewise, the chloride ions in the surface of the sodium chloride, they are subject to interacting with water molecules as well, because what happens is, again, the water molecule is a liquid. So the positive end between the hydrogen atoms, they can also interact with the negative charge of the chlorine, just like the oxygen did with the sodium. Look at that, isn't that amazing? And it actually does this. This is something that you can observe. Take some salt, put in some water, observe what happens. And what you'll see is that if you agitate it, if you stir it, these hydrogen atoms can actually rip the chloride ion off the surface of the sodium chloride, and then that will expose a deeper layer of the sodium chloride, and eventually the whole thing dissolves. Really quite remarkable. This whole process where these ions are surrounded by water molecules is called hydration. Hydration is where the ions are surrounded by water molecules. The water molecules are said to hydrate these ions. Now it turns out, if you do this, if you take this salt and you dissolve it into water and you put it in a little coffee cup, so you got, we would call it saline, salt water, right? And then you do the following. You take a couple of conductors with a light bulb and you attach a power supply to it. What will happen is the ions in the water can conduct electricity across those two and act just like a wire. And then what will happen is you'll get light coming off of this light bulb. Pretty darn amazing, okay? So essentially what's happening is the ions are conducting electricity in water. They only do it in water because they're able to move around with the water. In order to have electrical conductivity, charge has to be able to move around. So because they're in water and water is a liquid, these ions bounce around in there and conduct electricity, acting like a wire. So because of that, we call these ions electrolytes. Electrolytes, right? It's a good name for it because they conduct electricity. They're little particles that conduct electricity, so we call them electrolytes. As a side note, if you had a swimming pool and you had, let me actually erase this. If you had a swimming pool and you had pure water, you're somehow able to really purify the water. Oops. And it was distilled water, right? Distilled water. What would happen is if you were in there and there was a cloud coming by and you got that lightning bolt, right? People tell you, oh, if there's a thunderstorm, don't be in a swimming pool because you're going to die. Well, in a real swimming pool, you would. But if this were pure water, you'd be okay. Probably be okay, as long as you weren't too close to where the bolt hit. And that's because water is not a conductor. Water is an insulator. It doesn't conduct electricity. It's only when you put the salts in, salts are added, and those salts produce ions that are able to move around with the water, right? Like sodium chloride, for example. Now you have essentially a wire. Those ions can conduct electricity. So now you're in trouble, right? So obviously don't go into a swimming pool if there's a thunderstorm, but that's because of the salts that are in there. Now, lightning is pretty amazing, high voltage. It can probably actually even break down water. But water itself is not a conductor. So now what we want to do is we want to just take a look at some of the substances that we experience or we deal with in this course and their relationship to electrolytes. And the first one are what are called the strong acids. Table 4.1 shows what are called the strong acids. There's 7 of them: HCl, HBr, HI, H2SO4, HNO3, HClO4, HClO3. These are all called strong acids. And the reason they're called strong acids is that if you put them into water, the water essentially does to them what it does to an ionic compound. Breaks them up into ions. Does it very well, in fact. And so I'm showing you what ions they break up into on this slide. This one's a little different. It forms H plus and HSO4 minus. H plus and NO3 minus. This is called nitric acid. H plus. This is called perchloric acid. Okay, those are called the strong acids. So they will actually form a large number of ions, just like ionic compounds would. And so for that reason, these are strong electrolytes. Okay, so strong electrolytes, meaning that they conduct electricity very well because you're forming a high concentration of ions when you dissolve these acids into water. But there are also what are called weak acids. So those are the strong acids. Let me show you the weak acids, or at least some of them. An example is HF. Now, if you were to look at the equation, it looks the same, but only about 1% reacts or dissolves. Only about 1% of this. So 99%, let me actually write it this way. You get 1% this, 1% that, 99% is this. So only a little bit of it actually dissolves and actually forms H plus and F minus. Here's another one. It's called acetic acid. Oops. These are aqueous. Again, you get about 1%. So these are examples of weak acid. Weak meaning you're not producing very many ions. So for that reason, they're called weak electrolytes. They conduct electricity, but only a little bit. If you were to put a light bulb in a solution with one of these acids, it would barely turn on. You see a little bit of light because it's conducting a little bit. It's like a very poor conductor of electricity, so they're called weak electrolytes. Weak acids are weak electrolytes. There's another category of substances called bases, and I'm going to focus on what are called the weak bases. And these are compounds that have nitrogen attached to a hydrogen. So one of them is NH3. Here's another one, CH3NH2, C2H5NH2. There are many of them out there. These are some of them. Essentially, they do kind of a weird thing. They actually react with water. I call it weird, but it's actually very interesting. They react with water. I'm going to draw a double arrow here. I won't talk about what that means. But essentially what happens is the water donates an H plus to them, and you get ions. And the water is converted into something called a hydroxide ion. Very interesting. So this one's CH3NH3 plus, and then that's plus OH minus. And then this one's C2H5NH3 plus and OH minus. Now, you only, again, 1%. Only 1% of this is converted into this. It's still 99% for these ones here. So we call them weak bases. They're forming hydroxides, that's why we call them bases. They're weak bases because you only form a little bit of them. So you get some ions. Remember, these are charged. Those are ions. So these are weak electrolytes also. So that's a second category, this idea of weak electrolytes. So there's the weak acids, and then there's the weak bases. Those are both weak electrolytes. The strong acids are strong electrolytes. And then finally, we would talk perhaps about ionic compounds like sodium chloride. So ionic compounds form strong electrolytes. Okay, just like the strong acids do. Okay, so the idea here would be like sodium chloride. If you dissolve it into water, you get sodium ion and chloride ion. How do we know it's an ionic compound? If you have a metal with a nonmetal, that would make it an ionic compound. Okay, so sodium chloride dissolves into water, 100%. All the sodium chloride dissolves. So this is called a strong electrolyte because it's going to conduct electricity very well, right? Sodium, chloride, those are ions. They conduct electricity. If you dissolve it and you get 100% sodium and chloride, that's going to conduct electricity very well. So we have the strong acids, we have the weak acids, we have the weak bases. Now we have the ionic compounds. And now let's talk about these molecular substances. That's not going to be the focus of this chapter, but molecular compounds, the only ones we're going to consider are three categories. One is just water. The second one are what we call alcohols. And the third one are what are called sugars. These are molecular compounds. So alcohols are what we would say ROH. Okay, ROH means something like this. CH3OH, C2H5OH, C3H7OH. There are many of them out there, but those are three examples. So some kind of hydrocarbon attached to an OH. These are very soluble. They dissolve in water. Now, what about sugars? Sugars, you are familiar with perhaps glucose from chapter 3, and sucrose. From chapter 3. Those are examples of sugars. Sugars are also very soluble in water. They dissolve in water. And the alcohols and sugars both dissolve in water for the same reason. They actually have something in common with water, and that is that their structures are actually pretty similar. So if you take a look at the water molecule, and I'm just going to use it as an example, a simple alcohol, methanol. Water has an oxygen atom attached to two hydrogen atoms. And what did we say about this earlier? We said the negative is there and the positive is there. Okay, so it has a negative end and a positive end. Well, an alcohol has an OH, so it also has a positive end and a negative end. So if we take an alcohol which has an OH, okay, what happens is the H can interact, I'm sorry, let me rearrange this. Easy to make mistakes. The oxygen in the OH can position itself near this positive end here between the hydrogens. See, this oxygen here is negative, and this hydrogen is positive, so they can interact with each other, so they're attracted to each other. So the alcohol is actually attracted to water. And so another water molecule, for example, could interact here. There's a negative in there, so they're going to attract each other. So that's why alcohols dissolve in water. And sugars are pretty similar. Sugars are essentially combinations. They essentially have a ring with OH groups. So they actually have a lot of OHs on them. And so those OHs also can interact with water. They're attracted to each other, right? So this water molecule would be attracted to that OH group because the positive here could interact with the negative there, and the negative here could interact with the positive there. But you've got them all around that ring. So there's a lot of interactions there. So that's why they dissolve. However, they don't form ions. They don't react in the same way that sodium chloride. Sodium forms ions, so does the chloride. These ones are neutral. So alcohols and sugars, even though they dissolve in water, they are non-electrolytes. Okay? They dissolve in water, but they don't form electrolytes. They do not conduct electricity because they're molecular substances. There's the bonding that takes place between these atoms. Molecular bonds do not break, so there's no ions formed. Okay? So metal, non-metal, that's ionic. That's going to form strong electrolytes. Carbon, oxygen, hydrogen, if there's no metal in the compound, that's a molecular substance that is not going to form ions. Okay? So there's a nice little intro into our different types of electrolytes. I recommend that you look over the videos of identifying electrolytes. Sample problem 4.1 would be a good example for you to take a look at.